Welcome back to our series of math videos. Today's topic deals with properties of exponents and scientific notation. We continue the discussion that we had the other day on exponents and throw a few more rules in. So specifically today we're going to look at exponential notation when you're multiplying and dividing. We'll look at rules for power of a power or power of a quotient. And then lastly, we'll look at an example of exponents and scientific notation. First off then, the multiplication and division. So when we look at the product rule of dealing with exponents, it states that if I'm multiplying common bases, in this case the base is x, if I'm multiplying common bases that have exponents, to simplify this, I can add the exponents. So in this first example, I've got 2 cubed times 2 squared, common bases, therefore I can add their exponents. The answer is 2 to the 5th, or 32. Notice that I could have also evaluated it this way. 2 cubed is 8, and 2 squared is 4, and then 8 times 4 also gives me 32. Go ahead and do the next ones and see how you do. Press pause, do the next ones, and then press play again and see if you get them right. Common bases, add exponents, this would be a to the 14th. This one a little bit harder because I've got multiple factors in each one of these. But I can treat them, I just look for ones that are the same. So 3 times minus 5 is a minus 15. X squared times x cubed, common bases, add their exponents. So this would be x to the 5th, and y to the 4th times y to the minus 3, add exponents. 4 plus a negative 3 is y to the 1st, or just y. So that's the product rule. Common bases, add exponents. Also, if we look at the quotient rule, the rule is very similar. But this time, if I'm dividing common bases, I subtract their exponents. So in this first case, 2 to the 6th divided by 2 to the 4th, bases are the same, therefore I simply subtract the exponents. 6 take away 4 is 2, and 2 squared is 4. If I did it a different way, 2 to the 6th is actually, I'll write it over here, I think that's 64, hopefully, and 2 to the 4th is 16. And certainly 64 divided by 16 is also equal to 4. Okay, here's two other examples. Go ahead and press pause, see if you can do them. Okay, hopefully you've pressed play again. Common bases, subtract exponents. 5 take away 3 is 2. 9 take away 10 is a negative 1. Ooh, don't know if I like that. Well, we'll fix it later. Z cubed divides Z cubed. 3 minus 3 is 0. And we learned earlier that anything to the 0 power is equal to 1, just the number 1. Not an exponent 1, but just the number 1. So if I were to simplify this a little bit more, as we saw in the last video, if I have a negative exponent, I can express that as a denominator of a fraction, but instead of being a negative 1, down here it becomes a positive 1. And also z to the 0 is simply 1, which I could write like times 1 like that, or I really don't need to write it in. So my simplification of this would just be x squared over y. Similarly, in this last question, looks like 7 will divide into both of those, so 7 goes into 35 5 times, 7 goes into negative 14 and negative 2 times. Dealing with the exponents here, 8 take away negative 2 is 10. Do you see that? Let me just write it. It'll be 8 take away a negative 2. Notice that those 2 will cancel and it'll become 10. And then x, 3 take away 5. Careful with that. Don't say it's 2. It's a negative 2. So rewriting this, I could write it. The negative sign we usually don't leave on the bottom. Usually we put it on the front, on the top, or we are non-committal and put it in the middle. Either spot there is fine. So here I'd have y to the 10th on the top, and instead of x to the minus 2, like we did with this one up there, I would put x to the positive 2 on the bottom. And that would be my simplification of that. The next rule deals with something called the power rule. And it says that if I have an exponent that is raised to another exponent, I multiply these two exponents. And if I have more than one term inside of that bracket, every factor within that bracket, its exponent is multiplied by the p. Doesn't matter what the bases are, every factor that's within this bracket, the exponent must be multiplied by p. So here's some examples to try. This one, I've got an exponent inside a bracket and one outside. I multiply those two. So it'd be 2 times 3 is 6. Go ahead and do the next two and press play when you're done. Okay, hopefully you've pressed play. 3 times 4 is 12, so 2 to the 12th. I could figure out what that number is, but it's a real big number. I'll just leave it as 2 to the 12th. The next one, inside brackets, and then I have one outside. So every factor inside here must be raised to the 4th. Notice that 2 is a factor, x squared is a factor, as is y cubed. So they all get raised to the 4th. So it'll be 2 to the 4th, x to the 2 times 4 is 8, and y to the 3 times 4 is 12. And 2 to the 4th is 16. See, that one I evaluated because it was fairly small, but 2 to the 12th, that's a huge number. It's 16 times 16 times 16, which is too big. All right, continuing on. If I have a quotient within brackets, all raised to an exponent, just like the one we did before, everything inside the bracket gets raised to that exponent, as shown in this example. So for this question here, I have to multiply these powers, so it'd be 3 to the minus 4 over 4 minus 3 times minus 2 is a positive 6. Again, if I'm simplifying this, I would probably write it this way. 3 to the minus 4 I would put on the bottom and make it a positive 4, and then I'd have 4 to the 6 down here too. On the top, since I moved this down, there's nothing there. I can't write a 0 there, but typically I just would write a 1. Now if you want, you could figure out what 3 to the 4th is. That's 81. But then when you figure out what 4 to the 6th is, that's going to be a huge number. Same as 2 to the 12th. Real big number. You can figure it out if you want. But for now, I'm just going to leave it as 4 to the 6th. You could figure that out, times it by 81, so it's 1 over whatever that product is. Lastly, in this question, it's a little bit, I guess it looks very similar to the one before, just a few more numbers, a few more letters. When I'm looking at this though, it looks like I can simplify things in the bracket even before I raise them to that power. So maybe I'll do that. I'll simplify inside the bracket first, then raise to the power. That's how I would do it. And usually that follows our rules of do things in brackets. Okay, so 32 divided by 8 is 4. Y to the minus 3 and y to the minus 4, dividing common bases, subtract their exponents. So it'll be y to the minus 3 minus a negative 4. I had to write it like that. I couldn't do it in my head. But now I can see that that's a 1, y to the 1. And then z to the 2 minus 3, that's a negative 1. And all this is raised to the power of 6. So simplifying a little bit, I'd have 4, and then these two would change to plus, so that's 1. So it'd be y to the 1 and z to the minus 1. Let's put that z on the bottom. Z to the positive 1 on the bottom. Again, all that is raised to the 6th. So everything inside gets a 6. So 4 to the 6th, y to the 6th, and z to the 6th. Again, you could figure out what 4 to the 6th would be. I guess I should have done that because it's come up a couple times already. But it'd be a big number. I'm okay if you leave it like that, but you could figure out what that number was. One of the examples where we use exponents all the time is scientific notation. It's used to express very large numbers or very small numbers. So here's an example of one. The number of moles, or number of particles in a mole of matter, is 6.02 times 10, this should have been a 23rd up here, an exponent, times 10 to the 23rd. If I wrote that in decimal notation, it would look like this, 6.022, and then a bunch of zeros behind it. What we want to be able to do is convert between this decimal notation and exponential notation, or scientific notation. And it's really quite simple, because what we need to do is rewrite any decimal so that I have a number here that's between 1 and 10, can't be less than 1, and it can't be, I guess, 10. Has to be in between 1 and 9.99999. And then a power of 10 over here. Let's try a couple of examples. So here's what it should look like. Here, where m is a number in between 1 and 10. So let me just put that. So it's in between 1. It could be equal to 1. So m. And it has to be less than 10. And then here I have some exponent. Okay, so I looked up just here a bit ago what the national debt was in Canada, and it turns out to be this big number. And when I look at it, I don't know whether it's millions or billions or quadrillions or gazillions. But I can get a better handle on it if I change it to scientific notation. So to do that, what I do is I look at the number and I put a decimal after the first non-zero number. So after this one. So I'm going to write that as 7 point, and then I can write as many significant digits as I want. I'm just going to maybe put 2. So 7.2, and then I'll round this number. It's 5 or greater, so this one I'm going to put to a 6. Typically the question will tell you what kind of way to round that. And then I'm going to go times 10 to the, and here I indicate how many decimal places I had to move. So my decimal place currently is right there at the end. So I had to move 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. So 7.26 times 10 to the 11th. That's what this number is in scientific notation. I know that millions are 10 to the 6th. Billions are 10 to the 9th. So this is more than billions. Looks like it's 100 billions. So look at another one, a very small number. So the weight of a grain of sand. Probably grains of sand have different weights, but here's mine. Okay, if I wanted to change this to scientific notation, I come in here from the left and I look for the first non-zero number. There it is right there. I put my decimal right after it, and then write down any significant numbers after that. Then I accompany it with a power of 10. This time I'm moving my decimal to the right, and it's a very small number, so my power of 10 will be negative. Okay, large numbers, the power is positive. Small numbers, power is negative. So how many times do I have to move? 1, 2, 3, 4. So that's how I can change from decimal notation to scientific notation. Let's try going the other way. Here's some numbers in scientific notation. Here's one in scientific notation. This one, I guess, is decimal. I want to change that to decimal notation. So what I do is I take the decimal from where it's at. Since this is a large number, because it's positive, I'm going to move my decimal to the right. So I have 2 and then 3, 4. So I've moved my decimal 1, 2. I have to move it 3 more times. So I'll get 3 zeros. So this number could be written this way or as 234,000. This number, very, very small number, so I know I'm going to have times 10 to the minus something. I have to figure out what that is. Come here, here's my first non-zero number. I put my decimal right after that. And then include any other numbers that I think I need. There's only 2 here, I'll include both of them. And then tell you how many times I move my decimal. 1, 2, 3, 4, 5, 6. There we go. So that's how I can change numbers from scientific notation or to decimal notation or back. The last concept we'll do in this section is doing operations with scientific notation. These ones are ones where I can use the rules that I've used before with exponents. So here I've got 2.34 times 10 to the 5th, 5.2 times 10 to the minus 8th. If I'm multiplying these, what I can do is I can multiply the common things, like this one and this one. 2.34 times 5.2, let me just figure out what that is. 2.34 times 5.2, sorry, I should have got one that I could do in my head. 12.168. So it's 12.168 times, okay, 10 to the 5th times 10 to the minus 8. Common bases, I'm multiplying, add the exponents. 5 plus minus 8 is minus 3. Whoops. 10 to the minus 3. Now this sort of looks like scientific notation, but remember I said we had to have a number in between 1 and 10? So I really should change this number. Let's just look at this number by itself. And I can change it to scientific notation. It would be 1.2168 times 10, and I move the decimal one place, so it'd be 1. And then I also have that times 10 to the minus 3 at the end. Again, here I've got common bases, so I can simply write the number as 1.2168 times 10, and then 1 plus a negative 3 is a minus 2. This would be the correct answer for that product. Doing it with this one, oh, these numbers are, I guess they're very small, but I can change them to scientific notation. 3.2 times 10 to the 6 minus 6 divide, this would be 1.6 times 10 to the minus 3. So now I divide these two. 3.2 divide 1.6, oh, that's just 2. Times 10, subtract exponents. Minus 6 minus a negative 3 would be negative 3. So that would be my answer for that one. Okay, so we have gone through quite a little bit of looking at multiplication and division rules, or product and quotient rules of exponents. We also looked at the power rule over product or over a quotient. And lastly, we looked at scientific notation. I hope that this little scribblecast has helped you out a little bit. Do lots of questions in your book. Ask your instructor if you need more help. Thanks. We'll see you next time.